Thanks for stopping by Pete's Garage. Now we're going to talk about choosing a crankshaft. And this is not a very difficult decision, although some people do spend more time choosing a crankshaft than they do a spouse. But that's a totally different story. Alright, before we get into the detail, I'm going to give you a cheat sheet for choosing a crankshaft at the beginning of the video. First, you want a cast, forged, or billet crank. And is it made out of forged or billet material? Stroke length, main journal diameter, rod journal diameter, fillet radius, number of counterweights, method of heat treating, the crank snout size, what kind of windage treatment does it have, are there any lightning holes, what's the crankshaft weight, the rear main seal type, crank flange type, journal surface type, is it balanced, what are the material properties, is it a twisted or non-twisted forging, mass of inertia or the mass moment, snout keyway, and finally damper required. When you're choosing a crankshaft, there are a lot of things to consider, but let's try and keep it as simple and easy as possible so you know you're choosing the right one. First, what are you going to do with it? Is this a car you're going to drive around, beat on a little bit occasionally, and take it to cruise nights? Is this something you might race a few times a year? Or is this a hardcore race car, and then are you going to have a circle track, racing car, drag car, top fuel drag car, whatever? But for the majority of the people watching this video, you're looking for a performance engine, and let's call a performance engine anything over 500 horsepower. 500, let's call 500 to 1,000. And when you're choosing a crankshaft, you're going to be able to choose from 3 basic types, and this is the bulk of your decision-making process, is how it's made. And your choices are, it's either going to be cast, forged, or billet. The difference in these 3 is simply in the way they are made. For a cast crank, a mold is made, and the molten crank material, usually iron, is simply poured into the mold, creating the casting. Cast cranks are very easy to produce or mass produced, so they're very common in OEM applications. Now the cast crank is going to be made out of either iron or a nodular iron. The tensile strength of a common cast crank is going to be about 65,000 to 80,000 psi, which is relatively brittle, but it's perfectly suitable for general automotive use. An OEM nodular crank will have a tensile strength above 100,000 psi, which gives it better ductility and an elongation rating of about 3%. And this is suitable for truck applications and higher performance OEM engines. The deflection rating refers to how much a crankshaft can be deformed before it fails. Now, forged cranks are going to come in 2 basic types, twisted and non-twisted. The twisted crank is made during the manufacturing process where the piece of metal that's going to be turned into a crank is heated up, and that piece of metal is literally twisted into position, meaning the throws, the rod and the counterweights are all twisted into position while it's hot. This is the cheapest method of forging a crank, so that'll be the most common. The non-twisted forging is where the material is heated up and it is forged into position without twisting the crank. That's a little bit more expensive. However, the twisted crank, being the most common, really is going to be strong enough for most applications. Now, a forged crank can be made out of a variety of steel alloys, from 1053, 1045 mild carbon steel to all different kinds of alloys, which we're going to talk about in a second. But it's that wide variety of alloys that can go into a forged crank or be used to make a forged crank that allow you to choose a wider range of applications. Not only that, the forged crank is going to be stronger, and since it's let's say it's not as common as a cast crank, it's going to be more expensive. But as an alternative to buying a super expensive billet crank, the forged crank is going to be very reasonable and it's going to give you the strength you need. Next, we talk about the billet crank. Billet cranks are CNC machined from a solid chunk of high-strength billet steel alloy. They are typically the strongest and stiffest available and are the overwhelming choice for unlimited applications such as top fuel dragsters, pro stock, pro modified, and drag racers. Now, the billet crank, since it's machined out of a solid block of material, the real benefit of the billet crank is that it can be machined in an almost unlimited amount of configurations. Whether you're trying to maintain or obtain a large amount of stroke or a certain offset, or you want the counterweights machined a certain way to reduce windage or friction, whatever, billet cranks offer that kind of flexibility. However, they are by far the most expensive. So regardless of whether you choose a cast, forged, or billet crank, the quality of the end-up product really lies in the heat treating. When it's finished being machined, how is it heat treated before the mains and the pins for the pistons? How is it polished and how is it cleaned up? The heat treating is what determines the strength. So when choosing a crankshaft, there are a wide variety of materials the crankshaft can be made of. So let's look at them one at a time and see which might be best for your application. A regular cast iron crankshaft is going to have a tensile strength of roughly 70,000 to 80,000 psi, very common in OEM engines. Also, the nodular iron, a little bit more refined, a little more carbon in there, and gets the tensile strength up to 95,000, also common in some higher performance OEM engines. A cast steel crank, now we're getting into the, when you say I have a steel crank in my engine, it'll be a cast steel crank. It can have a tensile strength of up to 105,000 psi, and this is really the strongest casting of all the castings that are available. Now, we get into the alloys, or the combination of materials and forgings. There's 1010, 1045, 1053. These are going to get you in the 100,000 to 110,000 psi range. These are the more high carbon OEM forgings. And now we're going to get in more to the cranks, or the materials where you're going to have higher performance engines. There's a 5140 alloy, which is 115,000 psi, more for sportsman racing. The 4140 gets up to 120,000 psi, and that's really the premium forging alloy. That's one I use a lot, and I use the 4340 alloy, which is good from 140,000 to 145,000 psi. That is the best performance alloy. So I choose 4340 cranks when I'm building anything that's going to be 500 to 1,000 horsepower. Then we get up to the billet materials that are available for billet crankshafts. First, we have something like an EN-30B. That's going to get 160,000 to 165,000 psi. It's a premium billet. Then we get to the 4330M. That's 100 to 165,000. That's the maximum strength alloy, along with the 300M, 160 to 165,000, also maximum strength alloys. So along with choosing whether the crankshaft is cast, forged, or machined out of a billet, there's also a variety of materials within that. You can get a steel forged crank that's very strong and plenty good enough for your engine up to 500 horsepower, and it's going to save you money rather than stepping over into a 4140 or 4340 alloy steel forging. So there's a range there within the casting, the forging. Let's forget about billet because no one's going to be spending $6,000 for a crankshaft. And the regular, let's say, casting for a cast crank, you're looking at OEM cranks that are going to be like in the $200 to, let's say, $400 range, and then we start to get into the forged materials ranging from like $400 to $800, $900, depending on the complexity or the alloy used to make the crank. So now we talked about the types of cranks that you can buy: cast, forged, billet. We talked about the twisted, non-twisted for the forged crank, the billet crank, the flexibility of the CNC machining, and heat treating. I briefly touched on that. But here's something really to consider. Where is the crankshaft made? Where does the material come from? What mill? Where is the steel mill that made the material that goes into the crankshaft? That makes a huge difference. I've recently got involved with some material issues with a part, and I had two parts. One was made by material made from one mill. The identical part was made with material made by a different mill. And the material made by one mill, even though they're both made to a specification, an ASTM spec or a mill spec, whatever you're gonna, whatever it's determined that needs to be made to spec, the material made at one mill was not as, let's say, defect-free as one from another mill. It's just like a hamburger or any other food you buy. You can go to one place and get a high-quality steak, or you can go to another place and get a lower-quality steak. You can buy a ribeye at one place and a ribeye at another place. They don't taste the same. That's exactly what happens with materials for crankshafts. I strongly suggest that you look at and find out where the crankshaft is made, because crankshafts from China can be very attractive. You can, for example, if you wanted to buy a forged 4340 crankshaft and you have two crankshafts, one of them is made in the USA, one of them is made in China, and you're thinking, hey, they're both 4340 forged crankshaft. The American made one is $850 and the Chinese one is $650. Even though they're made out of the same material grade, they're not identical. There are ways to, let's say, adjust the smelting process, which is how they take the steel, how they melt it, and how they put the ingredients in, and how they clean off the slag, and how they purify the material before they pour it into the billet that's used for the forging. And that can make a huge difference. There's something in the material called inclusions. You can have inclusions or porosity. An inclusion is where you have a small defect in the material, meaning that while the material is being made, there's extra silicon in there, there could be extra carbon, nickel, something in there, and as the billet is made, you have this very small, it can be maybe 1,000, couple thousandths big, and it's going to be in the material, and that is going to weaken the crankshaft overall, versus another mill that has a higher purity rating when they make the material or smelt the steel. So if it's inclusion free, it doesn't have any foreign material in it, or voids, which are small air pockets, something like that, the better quality of the steel, the better quality of the crankshaft. So a 4340 crankshaft made in one place versus a 4340 made in another place are not going to be identical. And if you're going to be building a high dollar engine, you're putting your time, your energy, and your money into building something, looking and buying something cheap because it's the same number but it's cheaper because it's made in China, I really strongly suggest you take a look at that, because I've heard too many results where crankshafts have broken and it was a cheaper Chinese crank or an offshore crank that wasn't really made to the same specifications as a mill that might be in the United States, or I shouldn't just say United States, a mill that produces a quality steel versus a mill that's pumping out cheap, and they really don't keep track of the quality of the steel that they're making. So now after the crankshaft is made, it has to be heat treated, and the heat treating process is critical to the finished product and what you ultimately buy and how long it's going to last. There are some heat treating basics that we're going to go over real quickly, and depending on the crankshaft you buy, you may or may not be able to find out how it was heat treated. But in case you do, this is what you need to understand. After a crank is rough machined, it's baked to roughly over 1,000 degrees F, then it's rapidly cooled or quenched in water, oil, or some type of polymer quenchant. Now the crank is stronger, but it has little ductility or impact resistance, so it has to be relieved. The stress has to be relieved, or it has to be tempered, and that involves heating the crank again to a temperature roughly around 600 or 700 degrees F. Then the cooling process is controlled, and according to the properties of the steel, the cooling process will determine the final outcome of that heat treat. The final step after all the machining is hardening of the journals. Usually with a process called nitriding, and nitriding is something we can get into here, but basically it involves heating the crankshaft in a closed chamber oven, introducing ammonia, nitrogen gas, and that reacts with the carbon on the surface of the metal, and it hardens approximately 0.010 of an inch deep. Now when you're choosing a crankshaft, you won't necessarily have the ability to select the heat treating process involved, but it's good to know what the heat treating processes are, so if it is indicated in any of the specifications, you have a good idea of how it was made. This is why it's important to understand the heat treating process the crankshaft went through when it was being manufactured, and it all has to do with machining when you go to put it in. Now, if you're just rebuilding an engine and you're thinking, should I replace my crankshaft, here's something to consider. If you have a factory cast crank, that crankshaft can be remachined. Let's say you spun a bearing and you have a big groove and you need to recut the main bearing or main journal because you have a gouge. A cast crank regular from the factory, that can be reground. You can cut that groove out of there and reuse that crankshaft without jeopardizing the integrity of the heat treat. Now, once you get up to a forging, most OEM forged cranks are induction hardened. Induction hardening is when they take an electrode, put it around the journal, and electricity is passed through, which heats up that journal very, very hot, and it creates a heat treat that goes fairly deep. So on a factory steel, factory forged, factory cast crank, you can have those remachined and recut without really worrying about it. However, if you buy a billet crank and it was either nitride heat treated or tough treating, which is another kind of heat treating, you're only going to have 10/1000ths of an inch deep of heat treating. And if you have to cut something because you spun a bearing, or let's say you have a block that you really want to use because it's the same year as your car, and you're choosing a crankshaft to fit in that block. However, something happened and the main bearings or the main journals, they had to be remachined, the cap and the block, which means you need an oversized or undersized bearing, or something happened and you need to remachine the crank to fit in there. If you use a forged crank that was simply nitride heat treated and you have to cut it, and let's say you cut 5/1000ths off, you only have 5/1000ths left of heat treating, which is not very much. So understanding your heat treating is going to help you choose which crank to use when you're either rebuilding or building a new engine using an old block. Get those heat treating things straight in your mind and keep it in the back of your mind as you're choosing. Do I want the cast crank, cast steel, cast nodular iron? It's going to fit my horsepower, or is it going to be forged? I want a forged crank because it's stronger. The fillets in between the counterweights and the pins and the mains, you're going to have bigger fillets, so it's going to be stronger. But it was nitride heat treated, meaning that the heat treating is only so deep and I have to machine it. I might have to have it reheat treated after it's machined. Or you go with a billet crank and it's going to be heat treated to the point where it doesn't matter, it's custom made anyway. That's why knowing what kind of heat treating was used is important. So aside from understanding those basics, there are some more advanced options you may or may not have depending on the manufacturer of the crank. One of those is the design of the counterweight. Now the counterweight can be made, and the two separating factors here are it can be either made for ease of balancing, or it can be made for the loading on the main bearing. The counterweight ideally should be 180 degrees off from the pin. You have a counterweight here and a piston here. That ideally should be 180 degrees across, and that can vary depending on the manufacturer. You may or may not have an option on that, but the counterweight that you choose does play a role when you get to the point where you have to balance the crankshaft. Those counterweights can also be designed to reduce weight and windage. Now another option you may have depending on the manufacturer of the crankshaft is the drilling of the crank pin. The purpose of drilling a crank pin is to reduce the overall reciprocating weight of the engine. So if you're looking for a higher RPM engine, or you want to produce more RPMs, the easiest way to get there is to reduce the reciprocating weight of the crankshaft and the whole rotating assembly. And one way to do that is to drill out the pin. Now when you do that, you're not really jeopardizing the strength of the crankshaft, because in a forged crankshaft, with like a 4340 forged crankshaft, it's going to have very, very strong ductility. It's going to be really strong, and it can have elongation. Remember we talked about elongation? The elongation rating on a 4340 forged crankshaft can be up to 20, 22%, maybe 23%. So that crankshaft can deform a lot more before it fails. And a way to reduce the amount of elongation and reduce stress on the mains is to reduce the reciprocating weight, and the drilled main pin is one way to do it. Another thing you may hear about or have a choice with when purchasing your crankshaft are gun drilled mains. Now that is done just simply to reduce the weight of the crankshaft overall. It can affect the performance because the piston and the crankshaft, that acts as a shock absorber, and as you gun drill the mains, you're kind of, I don't want to say weakening, but you're reducing the amount that the energy that crankshaft can absorb. So if you're concerned about the yielding of the crankshaft, then don't worry about the gun-drilled mains. Now we can talk about the strengthening of the crankshaft. We talked about the strengthening through heat treating. We can have induction hardening, nitriding, tough triding. Those are all methods of hardening the crankshaft and creating the hard layer and how deep it will go. The other thing that has come up recently, and kind of a matter of controversy I think, is the use of cryogenics. A cryogenic treatment to a crankshaft is when they take the crankshaft and submerge it into something that's going to cool it to minus 300 degrees Fahrenheit. And the thought process here is to freeze the crankshaft, and by freezing it, it helps release the stress. When it's taken out and put into room temperature, let's say 70 degrees Fahrenheit, and it's allowed to slowly warm up to that temperature, all of the grain structure and all the stresses in the crankshaft can be relieved through that process. Previously, I'm going to say maybe 10 years or more ago, this was thought more to be of a snake oil kind of thing where it really doesn't do anything. But recently, the techniques and technology around submersing the crankshaft in something to freeze it, holding it there from 24 to 36 hours, and then controlling the temperature as it comes up to 70 degrees, have proven to have some small gains. So some real high-end engine builders will use this process just to get that little extra bit of strength out of the crankshaft. But for the 90, let's say 99% of us who are just rebuilding an engine or building one for the first time, there is not a huge benefit in paying for that kind of treatment. Some additional things. Many years ago, there was a concept of cross-drilled vanes where the lubrication hole in the crankshaft was drilled straight through, so you have a cross-drilled main shaft for oil. This was thought that, well, if I have two holes, you get more lubrication in the crankshaft through the main. But what we soon found out, or what racers soon found out, is that when the oil gets in the crankshaft and it's inside where it should be lubricating, as the crankshaft spins, the centrifugal force forces the oil out a lot faster, and sometimes the oil pump can't keep up, which could end up starving the bearings. So while the cross-drilled main is not necessarily a good idea, smaller holes on the pins or the rod journal are a good idea because that can boost high pressure. So when you are choosing the crankshaft, look at those dimensions of those holes and how the oil is going to go through the crankshaft to lubricate your engine. You also want to make sure that the oil hole where the oil comes out into the rod bearing and main bearing have an adequate chamfer on it. If you do not have an adequate chamfer on there, there's a possibility that the hole could shave the bearing, completely ruining your engine. Most engines, or most crankshafts come with proper chamfers on the holes, but take a look at it. Take a look at what they say about chamfered holes. Look at the picture and make sure it's there. It's really critical to having your engine last a long time. Another thing to consider is the crankshaft balanced? When you buy it, does it come balanced? If it does not come balanced, I would suggest having it balanced along with the entire rotating and reciprocating assembly. If you think about it, the crankshaft is rotating this way, which is your rotational energy, so it's got to be balanced this way to prevent vibration. The pistons are, while this is rotating this way, the pistons are going this way, which is the reciprocating weight. So when you're choosing your crankshaft, you want to see, is it balanced? If it's not, you're going to have to take it somewhere and have it balanced, unless you want to purchase a vibration damper or a torsional rotational balancer that's going to take care of the vibration of an unbalanced crankshaft. But if you can, get a balanced crankshaft, and even if you do buy a balanced crankshaft, I like to take the crankshaft and check it. Take it to a machine shop, say, hey, check my crankshaft, and while you're doing that, I'm going to take the rods and the pistons with me, with the pins and the entire rotating assembly. I want the crankshaft balanced for rotation, and I want all of my rods, pistons, and the reciprocating assembly balanced so that the entire assembly is going to be vibration free, which will not only add horsepower, because vibration is a huge theft of horsepower. Anytime you have vibration, that's horsepower going bye-bye. The more you can balance it, the more precise you can balance it, the more horsepower you're going to generate, and the longer the engine is going to wear, because the less stress you're going to be putting on all your main bearings and rod bearings, and the less the piston is going to be tilting inside of the cylinder. The rings are going to ride square. There's all kinds of geometry involved there. And I know that's beyond choosing your crankshaft, but the main point here is balancing. Buy it balanced, and even if it's balanced, just have it checked. Doesn't cost that much, and it'll give you great peace of mind. So like I said at the beginning, most people spend more time choosing a crankshaft than they do a spouse or a partner. In the end, it all boils down to the crankshaft for the application. Is it going to handle the application that you're putting it in? And that is the weight of the crankshaft. Is it heavy? Is it going to handle what you want it to do? The strength of the crankshaft, what is it made out of? Is the material going to be strong enough to support your application? And are you choosing it from a place that has material that's manufactured, smelted, melted, made, whatever you want to, the mill is making material that's of a good quality, which is also important. And then the application you're putting in, the strength, and is it going to perform the way you want it? And finally, buying a crankshaft, making sure you can purchase mating parts. If you have a block, if you buy a block, and the mains are drilled to a certain diameter, which require a certain size bearing, and you say, I want to use this crankshaft because I like it, if you can't find a bearing to match the crankshaft to the block, then you're not working together. You're not making a good decision there. So it's critical to work with the manufacturers. The OEMs, all the manufacturers, it doesn't matter what brand you choose, a SCAT, RPM, all the crank brands that are out there, Dart, Block, whatever you're going to choose, they all have really improved their technical support people. So if you call up a block manufacturer or a crank manufacturer and call their customer service or tech support and say, hey, look, I want to buy this crank and I'm planning on using it in this block. Are there any issues? They're going to help you because they want to sell their crankshaft. So work with the OEMs, work with the tech services department, make sure you're choosing the right crankshaft for your application, and when you're done, you will have many, many years of use and you'll be really happy driving the car. That's all I can say. If there's any questions, leave them below. We'll try and get them answered. I know this is a complex topic, and there can be a lot more going into it. My goal is not to tell you everything you need to know about crankshafts, everything about metallurgy and processing, but to give you a general idea how you can set some basic information or obtain some basic information to help you choose the right crankshaft for your application. Thanks for stopping by Pete's Garage.